Hey everyone, this is the first installment of an introductory series about the technical topics that gearheads will need to know about the electric vehicle future. Based on the investments happening in the automotive industry and the adoption rate of EVs, it's a foregone conclusion that EV technology will also permeate the automotive hobby and culture. I think this will be a great way to get the younger generation interested in cars. If you have any doubts about the EV revolution, just listen to what Jim Farley, CEO of Ford Motor Company, said on Munro Live about electric vehicle adoption.
Where do you think the crossover point is?
It seems to be going much faster than all of us forecasted. So it seems like, it's not a linear curve so far.
Welcome back to the Engineering Perspective channel. For those that are new, I've been developing automotive powertrain for many years and create these videos as a hobby. So if you enjoy this content, please hit that like button. The first two topics we're going to talk about are the overall architecture of an EV and some key details on batteries. The electric vehicle powertrain is made up of two main parts, which you're likely well aware of: the battery and the electric motor. While it sounds simple, the details can get quite complex. We're going to get into the key concepts you need to know to begin the transition to the EV performance vehicles. The battery consists of the cells, the battery management system, circuit protection, and the onboard charging equipment. The motor consists of an inverter, an electric machine, also known as a motor, and a reduction gear set. The rest of the vehicle is largely the same as any other car: suspension, steering, interior, etc. Of course, there's a lot of new technologies coming out. For the sake of this video, we're going to stick with the main powertrain components. Today's main focus will be on the battery. There's a number of items that can impact performance. Our main goal will be understanding the factors that can extract maximum performance from a battery. One of the most important terms to understand is C-rate. This is the basis to determine how much power can be drawn from or put back into the battery. A 1C rate means the battery would go from 0 to 100% in 1 hour. A 2C rate means it would go from 0% to 100% in 30 minutes. The C rate is used for both charging and discharging the battery. Why this matters is it determines how fast you can charge and how much power you can get from the battery pack. Let's look at a few examples. The Rivian R1T has a 135 kilowatt hour battery pack and a peak horsepower of 835, which is the equivalent of 623 kilowatts. So at peak power, the battery is discharging at a 4.6 C rate. The Model S Plaid has a 100 kilowatt hour and 750 kilowatts. So at peak power, the battery is discharging at a 7.5 C rate. And looking at a hybrid vehicle, the Mercedes-AMG GT63 SE Performance only has a 6.1 kilowatt hour battery. Relatively small, but it can put out 150 kilowatts in short bursts, which is a whopping 24.6 C rate. The rule of thumb is that the higher the C rate, the more attention needs to be paid to battery pack structure to minimize electrical resistance, improve cooling, and making sure the batteries don't overheat or damage themselves. This is also the reason why hybrid vehicles don't have as powerful of electric motors. Their batteries are relatively small and therefore can't put out as much power. The only way to improve the power output of the hybrid battery pack is to significantly improve its C-rate capability, which is what Mercedes did with their hybrid. So in summary, if you care about power, you need a high-energy storage battery optimized for a high C-rate. But that brings me to my next topic, which is battery cycle life. We all know batteries degrade over time and with use, but the number of times they can be charged is a key criteria when designing a battery pack. In many ways, this is no different than a cell phone or laptop. The way the industry measures battery life is by cycle count. You can think of this simply as how many times the battery has been drained and recharged. One cycle can be draining the battery from 100% down to 0, then recharging it back to 100%. Also, one cycle count could be draining the battery from 100 down to 50%, then recharging to 100%, and repeating it one more time. There's many combinations that can equal 1 cycle. Today's automotive EV batteries will target about 1,000 to 1,500 cycles before they're no longer useful in the vehicle, which means they usually go below 80% of their original rated capacity. However, some battery chemistries, such as LFP, can exceed 3,000 cycles. And to put it in context, if you have a 250-mile range battery that can do 3,000 cycles, that means 750,000-mile battery life. And given the battery technologies available today, there are certainly trade-offs between cycle life and C-rate. So when we start seeing extreme performance EVs, they will likely be trading off cycle life for improved C-rates. Next, we'll look at voltage. It plays an important role for the power of the battery. The basic relationship is that power equals voltage times current, so the higher the voltage or the current, the greater the power. One key item to know about lithium-ion batteries is that they have a certain voltage range that they work within. For a typical lithium-ion battery cell, it works between 3 volts and 4.2 volts. There are slight variances outside this range with different chemistries, but for the most part, 3 volts is 0% and 4.2 volts is 100%. Over and under voltage can cause damage to the batteries, so great care is taken to keep the cells in their operating range. It's one of the main roles of the battery management system. Once the individual battery cell details are known, the batteries are arranged in a way that achieves the goals of the vehicle. This means arranging the cells in series to increase voltage and in parallel to increase capacity. Let's take a look at a basic example. If we have 2 battery cells, if I put them in parallel, my voltage range remains the same, but I have twice the capacity. If I put them in series, I also get twice the capacity, but also twice the voltage. So if you want to get a voltage range to around 400 volts, you would need roughly 100 battery cells in series if we assume each cell is 4 volts. If you wanted to get an 800 volt battery, you would need 200 battery cells in series. If you've ever worked with remote control cars, drones, etc., you typically hear them talk about 4S, 6S, 8S batteries. What they mean is how many cells they have in series, and the more cells in series means more voltage. EVs are no different, they just have a lot more cells in series. You will commonly see battery packs called out in some S and P configuration, and it truly is as simple as it sounds. One last topic I wanted to highlight is charging. As we spoke about earlier, the C rate and size of the battery will determine how much power a battery can put out. However, one unique aspect about lithium-ion batteries is that they cannot charge as quickly as they can discharge. So if a battery can discharge at 7.5 C, like the Plaid, it may only be able to charge at a 2 or 3 C rate maximum. This is a key item to be aware of when you're determining how fast your car can charge and how much braking regen energy the battery can handle. Let me know in the comments what key aspects of an EV are interesting to you, and we will continue looking into other components in the next installment. Thanks for watching.